X is the instantaneous location, and spring is connected to the block, and the block is moved from this to that position. Work done by spring force will be integral F dot dr. Block is going to the right side, dr is dx, but spring force is opposite. So that's why vector F is minus k times vector x. Spring force is acting in this direction, whereas x is in this direction. X is in this direction, so minus kx. Dot product is gone. Putting the limits, we get minus kx1 square by 2. This is work done by the spring force. You can imagine that some external agent would be pulling this block. Block on its own is unlikely to go to the right side. So external agent may be pulling it, but we found out work done by the spring force. External agent could also be doing some work. Now here I must say that when I say F is kx, then it means that x is either the elongation or the compression. So it means that this is the natural length that we have considered. Only if this is the natural length can one say that F will be equal to minus k this x. If the length is not natural, suppose you have some spring like this, which is already stretched. Suppose it is stretched by x naught distance already. Its natural length is L. It's already stretched by L naught. Now external agent, due to external agent, it is pulled further by x1. Further by x1. Now in this case, the spring force will not be kx1. Spring force is k times the total elongation or the total compression, x0 plus x1. So if we have taken kx1, here I use x, let me make it x. So kx is wrong, kx0 plus x is right. Kx will be correct if x0 is 0. So in this particular case, when we found work done by spring force, initially the spring was at its natural length. Now one may ask, what if spring is not at its natural length? Well, suppose there already is some elongation. X1 is already some elongation, right? And we want to take it by some further elongation, so that finally it is L plus x2. That means we have pulled it further by x2 minus x1. Now in this case, L is the natural length. In this case, let x be some location like this. In fact, let me say some location where elongation is x, So elongation was x1 here, elongation is x2 here, and at some location elongation total is x. So if total elongation is x, elongation is x, so it will go from x1 to x2. So we would have half kx1 square minus half kx2 square, work done by the spring force. So see the difference. This is a case of initially having some elongation. This is a case of initially not having any elongation. And likewise for compression. Any questions? Let me know. Let me ask you this question. Suppose the spring is compressed initially, already compressed. It pushes the block and block moves to the right side. In this case, will the spring be doing positive work or will the spring be doing negative work? Yes, in this case, the work done by the spring will be positive. But if you compress the spring, maybe spring was at its natural length, so one should be able to handle all these variations. In this case, external agent will do positive work, but the spring force is on the right side. Displacement is on the left side. Spring force does negative work. Whenever we discuss with spring, work associated with spring or force associated with spring, you must remember that it is a variable force. So no question of FD cos theta. It's a variable force. You will have to go for integration. The problems in this topic are solved by certain techniques, and they are very few techniques. One, of course, is the definition of work based. You just go for this definition and you proceed further. Definition of work. Another one is using the work energy theorem, WET, which is actually work kinetic energy theorem. This theorem does not miss anything. W all means external, internal, all. And this theorem does not talk about potential energy. Actually, this theorem is enough to handle even the third point that I am going to say. This is capable of handling all problems which make use of conservation of mechanical energy. So third one is conservation of mechanical energy, which we will be applying later in a number of problems. Now, we have already discussed these two things. And regarding WET, I can say one more point that, as I said, it is all means all, internal, external, both. In Newton's second law, you see the word net equal to ma. That means when you have a system of particles, then A and B apply equal and opposite forces on each other. When you consider the whole system, then these become internal forces and they don't come into F net. They don't play any part in F net. They get cancelled. The forces that these two apply on each other. That is, internal forces do not appear in F net. When you talk of a system, it effectively becomes Fext. So one can wonder, why does it not happen in case of energy also? Why does it not happen in case of energy also, that W net, W all? Why doesn't it become Wext, just like it does in case of Newton's second law of motion applied to a system of particles? To understand that, consider two particles having masses m and m. Just keep them isolated from anybody else. Due to their gravitational attraction, they will rush towards each other, or they will move towards each other, right? Automatically. And when they move towards each other, this fellow gets kinetic energy, this fellow also gets kinetic energy. Now where is the external force? I said consider them as isolated, alone. Nobody else is there. So if nobody else is there can be no external force, but each one of them is gaining kinetic energy. So in W all, it is not all equal to ext. NET could be ext, Newton's second law of motion, when you're talking of a system of particles, not here anymore. Another example is two charged particles, one isolated, maybe plus Q or minus Q plus Q, whatever combination you like. And you will find that attraction, repulsion, whatever is the case, there will be energy, kinetic energy. This will also acquire kinetic energy, and so will this. If this is an isolated system, each one of them would acquire kinetic energy. From where did it come? W all. And where is ext in W all? 0. So all W has come from Wi and T, internal forces. So internal forces, work by internal forces cannot be cancelled just like that. That point you should make note of. Now, we were doing problems, and we would continue to do more problems. Here comes the first for the day. Whenever you see some frictional force, generally you should go for WET. Out of the two choices, WET and COME, when you see frictional force, you should go for WET. Well, I just think that there is some problem with this question, because when the car accelerates, then friction, while is responsible to move the car forward, does not remain in contact with a point. This point goes up. So frictional force does not move with the point. And when we discuss F dot D, then force should continue to act when the displacement is taking place. Then we say work is done. And here the point will lose contact, the point will come up. So there is some problem with this particular question. Now you may wonder, in that case, if friction is not doing work, then who is doing work? How does car accelerate? You get tired when you lift some heavy object, and some physicist tells you that you have not done any work because there is no displacement, but you get tired. There is something called internal energy, internal work. So sometimes it is internal energy which participates. Battery, for example. How can battery give some toy kinetic energy? Because battery has got internal energy, chemical energy. Now supposing we have opposite question. Now I had to add that thing, assume skidding. And the reason for adding it is that when the tire skids, when a tire skids, then the point of contact remains point of contact. It does not go up. And therefore friction continues to act throughout. This type of braking may be dangerous, but sometimes you will see in stunt movies that this type of braking is done so that car has to skid and then come to a halt. So you can find out the answer. Force is asked, plus or minus sign will tell the direction only. Plus or minus sign will tell the direction only. For a vector, plus or minus sign will tell the direction. For work, minus sign means something else. But here, force is asked. So, even if you just say it is 4,000 newtons, it's alright. And direction, of course, will be opposite to motion. Motion is here, force is here. Any questions regarding it? Let me know. This is based on V depending on X. So don't assume to begin with that force is constant. If it is constant, fine. But actually you don't need the fundamental definition approach to do this problem. Work done by all forces is asked. You should go for WET theorem. Try it out. ma square d by 2. That's the answer I have. And if you would like this to be discussed on the board, then raise your hand. Okay. Find the total work done by all forces. That will be simply change in kinetic energy. Change in kinetic energy is final minus initial. Final means a root x, but x has become d. Square of that. Initial a root 0, square of that. Just simplify, and if you have any question, then let me know. When we were talking about work done by gravitational force, then we said it would not depend on the path. If this is the trajectory, it can be visualized as this type of staircase, where stairs are infinity, right? So for this horizontal displacement, gravity will not do any work. Gravity is downwards. Such forces for which work does not depend on the path are called conservative forces. Work does not depend on the path. A contrast to this situation is in frictional force. Suppose some object moves on a table. Let's say the screen is a table. Some object moves on this table like this. Sliding. When the object is here, kinetic frictional force will act in a direction opposite to its velocity. It will act in this direction. When the particle is here and its velocity is in this direction, then kinetic friction will be in this direction. So it's like changing the direction as velocity changes direction. It's like changing direction as velocity changes direction. In case of gravitational force, it doesn't care about velocity. Parabolic path, projectile motion, gravitational force is always downwards. That's the major difference in the two situations. Gravitational force does not care about velocity. It's a constant force. It's constant force. Vector, direction also, magnitude also. Here, magnitude may be constant, mu times normal reaction. So it may be constant, but direction is the key. It changes its direction every now and then. So just think about this interesting situation. Some object falls from some height following this path and then lands on the surface of the earth. Now you may ask, why, how is it possible that falling is like this? Well, you can hold it and you can bring it with your hands. External agent grabs the particle and external agent moves his or her hand like this. That's how particle can be brought like this. As far as gravity is concerned, it doesn't care. It will just say, I am bothered about final and initial vertical distance. Not like this distance, vertical. mgh, that's it. Now imagine the same situation. Now this is the table, screen is the table, and some particle is sliding on the table following this path. Situation is same that way, but unlike gravity, which is having constant direction, friction will continuously change its direction, always opposing velocity. And that results in the h, the distance, not this h, but the total length of the journey. This point should always be kept in mind, that in case of kinetic friction, it could be the total length of the journey. So path dependence is there. You have seen path dependence in thermodynamics in case of gases. But there when we say path, we don't mean the trajectory of the gas. That will be really funny. When we say path, it means how pressure, volume, temperature, how will they change instantaneously. That's not the physical location. Here, it's a physical location that we are talking about. So path dependence, x, y, z coordinates dependence. There in thermodynamics, you can call it, instead of x, y, z coordinates, you can say PVT coordinates, pressure, volume, temperature coordinates. So in case of gases, work done depends on the path. In case of friction, in case of forces that are non-conservative. Conservative forces means work done would not depend on the path. Non-conservative forces means work done depends on the path. So as you will see later, for conservative force we define something, and that something makes us use the third thing that I was talking about. But when you have non-conservative forces, go for this. Wet. Yes, if it's a problem based on definition, then it's a different story. Otherwise, these two, which one should I go for out of these two, is a very common thing to wonder. So one should go for WET if there are dissipative forces. Dissipative forces or non-conservative forces. So let's take a problem based on dissipative force. That's your assignment question. If you need any clarification regarding it, let me know. Okay, so let me do one thing. Oh, looks like you are able to see it now. Okay. We stop at this point.